All right, so let's start with the programming stuff. We're going to start with ML100 down here. And what we're going to do is we're going to record these, we're going to program these things in Python. And you don't need to know very much Python to do this. And you don't need a Python environment. What we're going to use is Google Colab. All you need is a Google account. Log into any Google account, and you can now have these free online Python environments, and they're really very powerful. And this is great for teaching because every student has the same environment, even if they have a different computer at home or weak computer. So we're going to first just import TensorFlow, one of the many libraries used for machine learning. So I'll paste in that stuff. I think I have to use Command V to paste. All right. So this is just going to import TensorFlow and print the version. Now, when I start it, it's going to connect to a Google Compute backend and assign to me some RAM and processor time like a virtual machine. And then it'll run. It shows you how long it's taking to run down here. It should only take a few seconds. And then it's done. It's printed some version. All right. And any version is fine. I don't really care about the version. That just shows that it's able to access the TensorFlow library. So now let's consider a very simple problem. We're going to give it X and Y. We're going to have X go from -1, 0, 1, 2, 3, 4, and Y like this. And so a human could look at this and deduce the relationship. When X goes up by 1, Y goes up by 2. And when X is 0, Y is -1. So this is a linear relationship, and the relationship is Y is 2 times X minus 1. This is what humans do. They had the intelligence to take these examples of measurement and deduce the pattern. And we're going to let the machine learning figure out that relationship without a human inserting this equation. So that is the extent to which it's machine learning. It will figure out the pattern by itself, just from the data. So it doesn't take very many lines of Python to do it. This is going to make a model with one neuron. And here's the X input and the Y input, and it's going to fit. And it's going to use the default pattern, which is called stochastic gradient descent. What it does is it has two parameters, a slope and an intercept, and it starts them at random values. So if I get up here, let's try it there, just a little bit faster. All right. So if I go to the start here, it starts, and now it has a loss of 1.4. And what it does is it takes a partial derivative, so it gets the direction of dependence of each of those parameters and determines which direction will cause the loss to go down, and it takes a small step in that direction. So it started at 1.4, then it got down to 1.2, 1.1. It's just making little steps in the direction that will decrease the loss, like a ball rolling down a hill. And as you see, the loss gets smaller and the loss gets smaller. And after 500 steps of stochastic gradient descent, the loss gets really small, like 10 to the -5. And so it's pretty good. And now to evaluate it, I had it just predict what the answer will be for an X equal 20. And the right answer is 19. So as you can see, it's very close to 19. So the model worked pretty well, and it didn't take too long. This is what it looks like. You have X coming in. It's going to multiply that by M and add C, Y equals MX plus C, and it's going to fit these two parameters, and the right answers are 2 and -1. So we can also run it and predict the answers at the end. If you do it this way, it'll show the weights. Those things are called the weights, the parameters that fit it. So if you do it again, and at the end you print out the weights it finds. It doesn't like it for some reason. Oh, there it goes. Okay, it was just taking a while to get started. All right. So there we are. Here's what it learned: 1.99 and -0.99. So it's within 1% of 2 and -1. So it did a good job of fitting that perfect data, which it should. So now, suppose your data was not perfect, but it had errors in it. So let's go back and change this. All right, here's my data. I'm going to comment out this line just so it gets ignored, not really necessary. And there I'll have this data, and this data has just some random noise added to it. So if I try to fit that, then the loss is much higher. You can see it started at 17 or something. So 53, then it's rolling down, getting smaller and smaller, but the loss never gets down to 10 to the minus 5. There's no line that's going to perfectly fit that data, but the loss does get pretty small. It gets down to 0.04, 0.02, a pretty small number. And if I get to the end of it, it now has 1.99 and minus 0.99. So it still did a pretty good job of predicting the line that goes through that noisy data. Now, if you try to fit a parabola, which is not a straight line at all, then it's going to fit the best line it can, but the loss will stay very high. And if you want to see what it looks like, you can add some graphing code. And here we can try fitting a more complicated curve and graphing the results. So now what we're going to do is the data is going to be 0.1 x cosine x plus some random noise. So that's going to be a wavy curve. And we're going to use more than one neuron. We're going to have a layered neural net. First, we have one neuron coming in, which measures x. Then there's going to be 64 neurons in a hidden layer, and then another 64 neurons in another hidden layer, which do processing, and then one neuron on the output to be y. So this model is going to have a lot of parameters, and it's again going to fit with gradient descent. So if I run it, the first thing it's going to do is describe the model, and here you can see it. The first neuron has two parameters, slope and intercept. Then you branch out to 64 neurons, each of which has a slope and intercept. So that's another 128 parameters. And then each of those 64 goes to another 64. So that's going to be 2 times 64 squared, something like that, another 4,000 parameters and 65. So the first model was a straight line with just 2 parameters. Now we've got a lot of parameters, thousands of parameters, 4,355. And so here it goes. The loss starts at 0.3 and goes down with each step. And after enough training, as you can see, it does a pretty good job drawing a curve through that data. And you can now play some games with it. You can have fewer layers. If we decide we don't need 2 layers of 64 intermediate neurons, or at least we want to try it and see, we could comment out one of these intermediate layers. Get my mouse to work. There we go. Now it's going to have just one hidden layer of 64 to do the processing. So instead of having 4,300 parameters, it's now going to have only 195 parameters. So it's a much simpler model, and we'll see how good it is. And as you can see, it's not quite as good, but it's still pretty good. And you can play various variations here, and there's various flags you can get here. Now here, as before, there are flags to turn in. So if you run one of these, there'll be a screenshot with something covered up with a green mask. And that's when you run this and get that, that's the flag to turn in. So here's the name of the challenge, ML100.4. And the answer is what you'll see on your screen there when you get to this step. So give that a shot. That begins our Python coding part here. And you don't really have to do much coding. You just make minor alterations in the starting code I give you. So I'm going to stop this recording.